In this session, we'll try to understand a little bit deeper about the MOSFET in terms of its finite output resistance, which is observed in the saturation region. Now, once we are done with this particular theoretical aspect, we'll be able to understand, or we will be able to figure out that the entire operational perspective of the MOSFET has been understood. And then we can continue our entire exercise with the laboratory sessions. So now, what exactly we mean by the finite output resistance in the saturation? Because here, if you see, I have written the statement finite output resistance in the saturation. Now, before I proceed with that, let's try to understand and have a glimpse of the certain equations what we have dealt in the last couple of sessions. Now here, these are the set of equations which define the ID on the relationship between the VDS, or basically VDS and VGS. And here VOV indicates VGS minus VT. Now, if you observe, this is the typical equation that you basically observe, that is this particular equation. This is a reference slide which I have taken from the Cedra and Kenneth Smith textbook. So that's why the equation numbers are represented that way. Now, this particular equation is the condition where you see VDS is less than VOV. That is, VDS is less than VGS minus VT. So please do remember these set of equations whenever such kind of things happen. That means my entire MOSFET will be present in the triode region, or it will be in the linear region. So it is mu1 Cox WL VOV. VOV, I can replace it with VGS minus VT, which normally we do. You can write it as VGS minus VT minus 1 by 2 times VDS times VDS. So sometimes people club them and simplify it and try to rewrite this equation as mu1 Cox W by L VGS minus VT times VDS minus 1 by 2 VDS square. They mean one and the same. So this is basically the thing. Now, when we have VDS a little bit reaching to that of overdrive voltage, or typically when we have VDS greater than or equal to VGS minus VT, that means either it equals or it becomes more than VOV, then MOSFET enters into the saturation region, and that's how this particular equation comes into picture. That is 1 by 2 mu1 Cox W by L VOV square. Now there is further, like we told, upon further increase in the VDS, as per our graph, we say that there is not much incremental rise in the current is observed, but yet there is a small incremental current that we can observe over here. That is represented by something, this particular equation, where we try to represent this entire thing, this entire, or I can say as IB now can be represented as 1 by 2 mu1 Cox W by L VGS minus VT whole square times 1 plus lambda times VDS. This extra small term do comes into picture whenever we say that this particular condition is met. That is, when we further try to increase VDS beyond a particular voltage of pinch off. We usually, what I told yesterday, after a particular voltage, when the MOSFET enters into saturation, even though if you increase VDS, there is no much dependence on the dependence of current on the VDS, because as you can see in the equation, there is no VDS term is involved. That's why you can say that there is no dependency involved with respect to VDS for my ID. But if you observe the graph, practically we saw the graph was something like this. It was rising, it was not constant, it was rising little bit. So this small rise, whatever you can see over here, that is expressed by something known as 1 plus lambda times VDS. And this lambda term incorporate that incremental small change in the current. And this is what we are supposed to figure out what exactly this lambda term is and what is that entire process is all about, and why that particular small incremental resist or incremental current happens, and how do we represent those entire aspect in our entire scenario. So that would be our topic of interest today. So let's try to further proceed. Now, as we have seen in the yesterday's simulation process, we have used certain MOSFETs, and these are the symbolic representation of the MOSFETs. Typically, figure number B is the most common used practical scenario MOSFET, where we represent all the four terminals, including the body. So we know that there are three terminals: gate, drain, and source, but body is also being represented this way. And if it is an NMOS, we usually tie that to source, something like this, in whenever we do the lab sessions. But usually the arrow mark, wherever you can see, that is the point where you can see that there is a presence of the source. So this is how the symbolic representation of my MOSFET looks. Now, how do I identify, or how do I make sure that which is my source or which is my drain? Because like I told, MOSFET is a symmetrical device. So basically, if you see the structure like we discussed in the very first session, MOSFET is a very symmetrical device. Symmetrical device in the sense, you see from either way, the structure is going to remain same. So if that is the scenario, how do we make the designation of source and drain? See, it is basically by the polarity of the voltage where we apply. So the arrowhead, wherever you can see over here, that designate the normal direction of flow of the current. And that is how we say that the current is flowing from drain to source. See, although when we did our MOSFET physical the structural relevance of the MOSFET, we say that the current is flowing from source to drain, right? So that is basically your electron current. So if I consider the conventional current, which will be the opposite to that of the electron current, and that's why I say that the current is flowing from drain to source, and that's the reason I usually represent the current as IDS or sometimes ID. It means one and the same only. So we normally do not represent it as IS, but yes, that means IS and ID both represent the same current, because one is represented by the electron flow and another will be the whole flow. In the whole flow, in the sense, the conventional direction. So that's the reason why we represent the direction in this direction, from drain to source, and that's why the arrowhead is pointing something like this. So this is basically how we try to represent the arrow marking or the marking of my MOSFETs, which we can potentially use in our laboratory based sessions. Okay, now let's try to understand why that delta term, or how do I replicate, or how do I represent that particular small incremental resistance or incremental value of my current here in the saturation region. So if I see, this is ID versus VDS for a particular VGS. This is for a particular VGS. Like that, if you see here I have written multiple ID versus VDS for different value of VGS. As you can see, VGS is, I have some values for different values of VGS, and these are very idealistic graph. So basically, I say that beyond a certain point, when it reaches the saturation region, I say that there is no dependency. So basically, I say that in the saturation region, the drain current is only dependent on VGS, but it is independent of VDS. So when I say such an idealistic scenario, in such scenario, so basically I can consider my MOSFET being as a voltage controlled current source in the saturation region. So typically in the saturation region, if I do not consider the small incremental change in the current, and if I consider, like, if I ignore that small incremental rise in the current in the saturation region, and I consider there's a flat curve, or I say that if there is a current which has reached the saturation region and current has been retaining constant, that means my this particular MOSFET in the saturation region is going to behave as a voltage controlled current source. And how do I say that? Because current is a constant here in this region, and it is controlled by which particular voltage? VGS. So hence I say this particular MOSFET will be going to behave as a voltage controlled current source, and this is basically the key for the amplification process. So when I say that my MOSFET is going to behave as a current source in the saturation region for a fixed value of VGS, I can make use of this MOSFET as an amplifier in my saturation region of operation. And that's how the one of the major application of the MOSFET comes into picture in the saturation region, which is my amplification process. One of the other application is what? It is going to behave as a switch, on-off switch. Basically, when channel is formed, I say it is an on switch. When channel is not formed, it is behaving as an off switch. That is altogether a different application. Now, with respect to the major application in the entire analog design, which is my amplification, I see that my MOSFET has to be in the saturation region. But the scenario is here, if you want to achieve an amplification process, if you see here, if you see this particular equation which is in the saturation region, so this is basically equation in the saturation region, and here I am still considering there is no incremental rise in the current, and current is going to remain as a flat in the saturation region, or basically I'm trying to ignore a small incremental rise in the current. Okay, now if I consider that particular scenario, and if I consider saturation region equation, now if you see, like I told, this is the basis for my entire amplification process. Now if I just look here and try to figure out basically what I told, for an amplification to happen, the current has to remain constant, and basically the MOSFET will be behaving as a voltage controlled current source. And what is that voltage which is controlling my MOSFET here? It is the VGS. But if you observe the graph of VGS itself, right? This is my graph of VGS, if you can see over here. Now this graph is a very non-linear graph. What does that non-linear graph indicate? You see here, this graph, it is not linear in the sense, see, always remember certain things. Like for example, if I have a graph like this, a simple example, I have x-axis, I have y-axis, and let's say I have a linear graph which passes right through the origin. And let's say that if I pass some input here, if I pass some input onto this XY graph, then I can say that whatever the output I'm going to obtain here, see, if I say, if I'm going to pass an analog signal, because since I'm talking about amplification, let's pass an analog signal, and then the output, whatever I'm going to observe here, would be a completely unclipped waveform. And now the slope of this particular line indicates whether there will be an amplification or a attenuation. Like for example, if I consider one more simple graph, I'm not talking in terms of any particular uh, device. It's a simple graph I'm talking. So if I consider a graph, now if you see, this is also still a linear indicates for every incremental rise in X, there is a, um, perfect incremental rise in the Y, and it passes through the origin. Now, if I just pass the input and I give the input onto this particular line, I'll tell you what is this when I say I am passing the input. I'll tell about that. Then if you observe, see, if I just see, this is my input signal and the output would be and little bit more in size, in the sense the output is the amplified version of the input. So basically, if I want to ensure that there has to be certain amount of amplification to happen, then the graph has to be linear, no matter whether it passes through the origin or not, but it has to be linear. Now, what exactly I mean by it has to be linear, and how do I say that the amplification process works? Let's try to give little bit fair enough idea onto this, and then later when I talk about the amplification process itself, then I'll talk in detail about that. But let's try to give an input. Now look here. So this is basically VGS versus ID. Now, if you observe, let's try to plot some graph. Just try to give you some glimpse about the amplification process itself. Carefully observe. Now, let's say that, see, basically, this is my MOSFET, and let's assume that I have given certain amount of VGS and I have given some amount of VDS also, and as a result of which this MOSFET has entered into saturation region, because I want to figure out, or I want to see that how my MOSFET is going to behave as an amplifier. I'm taking in a simple single MOSFET. So I have given a VDS and I have given a respect to VGS, satisfying the condition VDS greater than or equal to VGS minus VT. And that means this MOSFET is now pushed into saturation region. Now, this kind of scenario where you try to ensure that a particular MOSFET is pushed into a particular region, that particular concept we call it as a biasing. Normally, you might have heard about these things, biasing a particular transistor. What does that mean? Biasing a particular transistor means you are giving some appropriate voltages such that those voltages will push the MOSFETs into a designated zone. So depending on what kind of voltages you are giving. Now, if the voltages satisfy this condition, that means my MOSFET is pushed into saturation region. Now, if I want to amplify a particular signal, let's say that I'm applying two voltages here. I'm just giving a raw concept over here, a detailed concept of amplification. I'll deal it in some other class just to give you the notion of the linearity concept of the graph and why the graph has to be linear. I'm trying to give you a brief about these things. So let's say that I'm giving two voltages. One is a DC supply and one is AC supply. So why two voltages? See, DC supplies are always given to ensure the biasing. That means the role of the DC supply is to make sure that MOSFET enters into saturation region. And once the MOSFET enters into the saturation region, you do not alter these DC supplies. And then you also add AC voltages. Why you give the AC voltages? Because you want to amplify. So amplification process can be clearly understood with the help of AC signal, and that's the reason you are giving the AC signal. So here the AC signal is a small signal. And when you see the output, let's say I'm taking an output from here. If I see the output over here, I should be able to see an amplified version. Now, how I can see that and how this graph becomes very relevant. Okay, let's see that. So this is the background of what I'm going to explain right now. Now, let's say that when I try to push my MOSFET into a particular a region of operation, let's say that I have given a particular this value of VGS, resulting in, let's say, this much amount of current. So this was the value of VGS resulting in the this much amount of current. And how do you get the voltage out of this entire thing? See, because MOSFET here is basically voltage controlled current source. Basically, the outcome of the MOSFET is the flow of current, which is the output. I can say is a current. Current is basically the final outcome. But how do you convert that current in terms of voltage? What I can do, I can just simply attach a resistance over here. I can attach simple resistance over here. So by doing that, I'll just write. So if I redraw the structure, something like this. So I can be seeing the output over here. So if my current through that particular MOSFET passes through that resistance, then I into R, I can get the outcome as the voltage. So that's how I can convert the current into voltages. So obviously, if I know any one particular term, I can get the other terms by just using the resistance. Now let's say that you are pushing in certain amount of VGS and you are obtaining this particular amount of ID, and this ID gets multiplied with the R. giving you the respective voltage. Now the point, and now if you just draw the, if you just draw a particular value, if you just figure out this particular id and vgs, you're going to get that particular value of v naught. I'm also going to change my particular voltage to a next level. Let's say that now I'm going to give the next level of vgs. I'm going to observe another particular current, and I'm going to multiply that current with a resistance, and finally I'm going to see that I'll be able to see another voltage. So like that, I can be doing multiple set of VGS, because here my VGS is the input and I naught is my output. I naught multiplied with R would be my V naught. V naught is also output. So basically, this is my input. X axis is my basically the input, and Y axis is the output in terms of current. And when that current gets multiplied with the resistance, becomes my output in terms of voltage. So basically, this is the graph of input versus output. Now, if you observe carefully over here, the maximum output can be observed at a particular point where the graph is linear, like I told here. If I just compare the plot of these two graphs, if you see, if I just try to plot input somewhere over here, exactly here, if I give the input and if I try to take the output would not be an amplified version. The amplified version of the output can be observed only at a particular point, and at that point when you give the input and take the output, and you can observe that the outcome will be a maximum. See, if you see, if I just give the input here exactly at vgs, and I can take the output like this, and it will be an amplified version. The same case if I just do it over here, if I give the input over here, and if I try to take the output, it may not be the perfect amplified version, or it may be a smaller signal, or it may be the signal exactly equal to the input only. So this is basically the linearity concept means. So the graph should be linear, indicates that to get a maximal benefit without any clipping of the input waveforms, I should ensure that the graph of VGS versus ID should be linear. But unfortunately, this is the characteristics of the MOSFET itself is like that. I cannot change the graph, right? I cannot modify the graph because the basic the structure and basic outcome of my VGS versus ID itself is like that. So that means I cannot modify the graph. So what I can do is I can just figure out a particular region where my particular graph is almost linear. In the sense, see, if I say this is my graph, so if I just try to draw a slope like this, I keep on drawing the slope, or like let's say that in this entire graph, let's say I keep on drawing up one particular line. If I keep on drawing a line, which is a slope, small slope, and try to figure out the slope, if I keep on drawing small slopes, and then if I try to calculate the slope, how do I calculate the slope? I just take, this is y, this is x, I do y by x. So whichever slope I'm going to get a maximum slope, that slope will be almost will be resembling to this particular line, where this particular graph which I am showing here in the below, where I obtained a maximal amplification or maximal benefit out of this particular graph. So again, if the graph would have been like this, then the output would not be in amplified version. So I'll try to find the slope. Again, how do I find the slope for any particular line? I just take the y divided by x. If I do that, I get some value. So wherever the slope is maximum, I'll consider that particular portion of the graph and I fix that particular portion. Let's say I'm fixing up this particular portion where I see that the slope is maximum, and this particular point where I'm fixing my VGS to get the outcome as I naught, that particular point we call it as a operating point, which we usually come across in even in the diodes or even in any devices. So what is the operating point? Operating point is a small particular point on an input graph, or basically on an VGS versus ID graph when I talk about MOSFET, where when you give the VGS, it is going to give you the maximum benefit in terms of current, and that current when gets multiplied with resistance is going to give the maximum benefit in terms of output voltage. So that particular point can be identified through a load line analysis or through some other aspect, but in a simple way I can just keep on bifurcating or differentiating this particular entire bigger curve into smaller chunks and finding the slope out of which, and the point at which I'm going to get a maximum slope, I can consider that particular point and say that that's where my particular graph or my particular point, where if I give that much amount of VGS, giving me that much amount of particular value of I naught here indicates ID, then I can say that I can fruitfully make use of this MOSFET as an amplifier. So this is basically the concept of linearity or non-linearity that is really important in any electronic systems. But here, because the graph itself was non-linear, I try to figure out a small region in the graph where the graph is linear. So I don't need the entire graph. I need a small portion where I just give that particular voltage at that particular point where my graph is linear, so that my entire MOSFET now becomes a linear kind of thing only in that particular region. So this is basically the concept of how the amplification process works. In detailed aspect, I'll talk about later when we deal with MOSFET as an amplifier itself. But this is how a small glimpse on the amplification process or fruitful outcome in terms of that particular linearity aspect. Fine. Now, now I just want to say that till now I said with respect to VDS versus ID, here the graph was having a small incremental rise. Now I need to even represent that small incremental rise in the current. If I now just take the slope of this particular portion, or if I just see that there is a small delta change in the ID, right? For delta VDS, for every delta ID and for every delta VDS, that is for every small change in VDS, as the VDS keeps on increasing, there's a small incremental change in the current, and that small incremental current we can represent as a small resistance. Basically, how can I see? This is a small incremental delta VDS as you keep on increasing beyond a particular value of saturation. And for every small increase in the VDS, there is a small rise in the current, which gives you to a small rise in the current. So if I do this particular thing, V by I, delta VDS by delta IDS, I can say that there is a small resistance that is observed in the saturation region, and that is basically your the finite output resistance in the saturation region. But now there is, if you observe, there is even a resistance that is observed in the linear region also. See here, the current is not rising very smoothly. There is a small, see, how do we say that the resistance is zero? Whenever you apply a voltage, if the current ideally increases like this, then I can say that it is the ideal value. The current is rising very quickly and there is a resistance of zero. But if somewhere if the graph is tilting, that means there is some sort of resistance that is observed, right? So even in this particular region, even in the linear region also there is a resistance, but that resistance is represented as RDS, which we saw in the earlier session. But now what I'm trying to talk about, that particular resistance is a small resistance, and that small resistance is basically represented over here when I try to model my MOSFET. When I say that a MOSFET is modeled something like this. Why it is called as large signal equivalent model, and why this, what is this modeling is all about? Let's try to give a simple thought on this. See now, if you see, if you whenever, let's say that I give an example like this. I give a circuit like this. I'm just giving you a glimpse on what exactly we mean by modeling. So let's say that I'm giving a particular example of a simple. I have a source of 5 volts, then I have 1 kilo ohm resistance, then I have, let's say that a dependent voltage, a dependent current source, then I have a capacitor, then I have one more resistance, and here one more resistance, then I say this is my simple network. Now, if I ask you to do the analysis of this network, you possibly will apply either of KVL or KCL. So you apply KVL or KCL and you form the loop over here and you try to analyze this entire set of circuit by appropriately applying those entire KVL or KCL, right? You find the node voltages and the loop current. But now let's say that if I give a scenario like this, I have a supply, I have a resistance, and I say that there is a MOSFET that is present over here, and here I am connecting some voltage, and now I am connecting a diode here, and then finally a resistance, and then this circuit is completed, and here let's say that a supply is given like this. Now, if I ask you to analyze this network, which involves the active devices, now till now we saw that networks can be solved with a passive devices by simply applying KVL or KCL. Now, let's say that if there is an involvement of an active device, now applying KVL and KCL here would not be feasible thing. So I should convert these entire active devices into their respective passive components. And this is where modeling will come into picture. That means this MOSFET can be replaced with something what is known as this particular model. If you see over here, this model, wherein you can see the MOSFET, like I told, it is going to behave as a voltage controlled current source. That means it is going to behave as a dependent current source having a value of 1 by 2 kn dash W by L VGS minus VT whole square. And there is a small resistance observed in the saturation region, that is a small incremental current is also observed. I'm talking about the practical scenario. So that means if I consider this as my gate terminal, this as my drain terminal, this is my source terminal, between drain and source, see, where did you observe the channel? If I say again the MOSFET here, it is between source and drain only, right? Between the source and drain the channel is there, and after the pinch off the channel gets tapered. That means whatever you are observing, a small resistance that is being observed, it is in the saturation region and it is between drain and source. That's why between drain and source the current of this much nature is flowing, and that current is a dependent current with a small resistance offered in the saturation region represented by the small r, and with a gate terminal connected like this. So this is basically a model of a particular MOSFET, which we call it as a large signal equivalent model. Now here, whenever if I want to solve any network based question, I can replace this MOSFET with this particular model, which can be seen over here. So that means if you see this particular MOSFET, I have a gate, I have a source, I have a drain. So wherever you have a GDS, just try to connect that over here. And now if you see this entire MOSFET, or if this entire new network would be changed into completely passive component. So that's how you can just try to apply your KVL and KCL. So is the case with your diode. Diode also comes with its own model. You can replace that with that particular model. So that is how you can see this particular thing is observed. And one thing you can see over here, there is a, if you see, there is a gap that is shown over here. This gap between gate and between drain and source. See what, how is the gap is shown? If I just try to remodel this, it looks something like this, right? I have a source, I have a drain, I have a gate, and there is a gap shown over here. This gap indicates that there is a presence of an oxide layer, which is an insulating material, and that means that there is no flow of current whatsoever may be the case, and that's why there is no connection being shown over here. Although when you write and push this into this network model, you can show it this way. If you connect it this way, then you have to mention it as Ig is always equal to 0. If you do not want to write Ig equal to 0, then better not connect it. So that is how the modeling is given. So this entire small incremental change of Vd, whenever there is a small incremental Id happens beyond a particular voltage of pinch off, that means during the saturation region, I can say that there is a small resistance is observed, and that is modeled something like this. So this is basically how your entire modeling of your MOSFET looks. Okay, now let's not get into this. I'll talk about this sometime later. Yep. Now let's try to give you the physical glimpse of what exactly happened over here. Like I was telling, between the source and drain, even if you increase the VDS beyond a pinch of voltage like this, beyond this portion, what happened? This particular channel was eaten up by the extra depletion region that was caused towards the drain, and as a result, the length of the channel got altered, or the length of the channel got decreased by an amount of delta L, because earlier my length was L, now my length got changed to L minus delta L, because this portion was eaten up by the reverse biased PN junction that formed towards the drain, and as a result the channel got its length reduced. Now this entire process, whatever we saw, give rise to what is known as a small incremental current in the saturation region, and that also means that there's a small finite output resistance that is observed in the saturation region, and as a result of that, I'm going to represent my MOSFET in terms of its model something like this, with a dependent current source and a small resistance R naught. See, R small, 0 small, R naught indicates a small output resistance or small finite output resistance in the saturation region only. Remember, RDS is in resistance that is observed between drain and source in the linear region only. There is a difference when I quote these two resistances. Please bear it in mind. So here I'm talking about R naught. So this is basically how exactly, with the help of a large signal equivalent model, I can depict the variation of R naught, or the variation of small current with respect to a voltage in the saturation region. And to represent this small incremental change, or to say that there is a small dependence on VDS with the ID. Earlier, what was the quote? I said that as per my equation, see, this was the equation. I told that when VDS is more than VOV, I said that nowhere in the equation, this is my saturation equation, nowhere in my saturation equation you would be observing VDS, because that's what my quote was. Because drain current is constant, and even though you increase my VDS, there is no further change in the current is going to remain constant. That means there is no dependency of VDS on ID. But practically that is not the case, and to ensure that practicality, I'm including a VDS term along with the term delta, and this delta term is known as channel length modulation term. Channel length modulation term. So that is my how much change happens to my channel, or how much dependency is made with respect to VDS in the saturation region for a condition VDS very more than VGS minus VT. So that means, see, when you just increase small VDS, I can still go ahead with this first equation where I say that the current is not dependent on VDS. But if you keep on increasing VDS further, that means that I can claim that my ID is totally depending on VDS. For a very small increase in the VDS, there is still a small rise in the current, and that is represented by the term delta. So that's what is mentioned over here. So what effect will increased VDS have on N channel once pinch off has occurred? So basically, this voltage accelerates electrons as they reach the drain end and sweep them across the new depletion region. Basically, what is happening when you further try to increase the VDS, the depletion region over here tries to increase and channel tries to taper and the length of the channel further decreases. And this entire change in the length of the N channel, basically the decrease in the channel, what we call it as a channel length modulation. And this is the most important point over here when it comes to the finite output resistance, or whenever we talk about the operation of MOSFET in the saturation region. Okay, that's about this particular thing. Yeah. So now let's finally wind up this with respect to how exactly my R naught expression itself looks. So basically, when I say R naught, what is the expression of R naught? So remember, to calculate RDS, I have to take equation of ID in linear region and I can find RDS. Now to calculate R naught, basically what is R naught? R naught is nothing but again a small change in ID for a small change in VDS. That means I can say that basically delta VDS by delta ID, that's my R naught, and that's what is been written over here. The reciprocal of dID by dVDS. Why I am taking ID by VDS? And there's a reason, because I need to start my entire analysis with my drain current, right? So basically R is my resistance. Resistance is represented by the term V by I. So R naught I can represent as for a very small, if I write this way, that means what will be the impact of VDS on ID? That means for incremental value of ID, how your VDS behaves, that becomes this particular equation. So that is the reason I'm not considering this way. I consider this way. So that means what is a small incremental change in the ID? Let me write here. What is a small incremental change in the ID for a small incremental change in the VDS? And if I take the inverse of that, that becomes my R naught. So fair enough. I'll just take an equation of my ID, do the differentiation, and once I do the differentiation, I can ignore this 1 plus delta VDS term because dou VDS term will be equal to 1. So I can just retain the delta term. So this becomes my dou ID by dou VDS. And if I want to get the resistance out of which, I just take the inverse of that. That becomes the inverse of this particular thing. So this is my R naught equation. So sometimes this R naught can be even represented by this particular equation, VA by ID. I'll talk about that now. So basically, this is how the derivative of the entire drain current equation, if I do, that's how my R naught equation comes. Because I need to say what is the small change in ID for every small change in VDS. So to do that, I have to uh, do the derivation of that. So when I do that, when basically I need to do the differentiation of that particular thing. So when I do the differentiation of that, I'm going to obtain this particular term, and the inverse of that would fetching me the value of R naught. So that is how my R naught equation is represented. So this is really important because we are going to calculate this R naught in our next session practically. And we want to observe what is my finite output resistance and how do I keep it, how do I change it by changing the WL, VGS, VDS, what impact it is going to have. We'll try to observe every single aspect on this R naught in the immediately next session. So if you see, so if I just see this particular graph, basically I told about one particular term over here. So I represented R naught. See, I can represent R naught either by this graph, or I can also represent it by 1 by lambda times ID, or I can also represent by capital VA by ID. So basically R is what? My V upon I. So I know that you can, if I know all the mu and Cox W by L, overdrive voltage lambda, I can represent this way. And this is the most appropriate equation because we figured it through the differentiation. Or I can remodify and structure it and write it as VA by ID, where I'm directly writing an voltage in terms of a new voltage, which is my VA upon the drain current. Now, what is that VA? VA is something, if I just imaginarily drag this particular graph and try to meet a particular one point, I get a particular voltage, and that particular voltage I say it as a VA, or sometimes also known as the early voltage. So that is basically the representation of this VA. So otherwise, we will usually go with this particular equation, and this VA is nothing but, so it is an imaginary line that we say. So like here it is mentioned, the VA, it is the process technology. So basically VA here, it is not under our control. When I say it's a process technology, it is being catered, or it is being taken care during the process of fabrication itself. So that is basically your VA. So but otherwise, my R naught equation is this particular term. So this is basically the entire gist of how the finite output resistance during the saturation region would look like. So basically there are two resistances that are observed in my linear region, or basically in my triode region and in the saturation region. In the triode region, it is the drain to source resistance, and to obtain this RDS, you have to look into the linear region of equation or triode region of equation. And R naught is a small resistance that we observe in the saturation region beyond a particular value of VDS. If I increase VDS to a larger extent, and to get that particular thing, I need to differentiate the drain current equation, which is observed in the saturation region, by including this term lambda. So if I do this, whatever the equation I'm going to get, that is going to fetch me a small R naught. So we're going to see both these things along with the slope things, which I showed over here. I remember I talked about length and breadth about this slope. So this particular slope I was talking, right? Operating point. So this particular slope. So we do give a particular name for this particular slope. So I told a particular slope, whatever we observe over here, at that particular point, we call it as an operating point. And I told that we have to calculate the slope. So that slope particularly we call, or we represent it with the term GM, and it is called as a transconductance. So whatever the slope we take on the ID versus VGS, that particular slope is itself basically known as transconductance. So henceforth, when I say transconductance, the immediately that one thing should come to your mind is, it is that particular slope on ID versus VGS, where if I apply a particular voltage and fetch a particular current and multiply that with a resistance, I'm going to get a maximum benefit out of it. So that is basically the indication of the transconductance. So more on to all these things, we'll talk in the subsequent session. So we'll try to see these entire thing in a simulation perspective. Okay, so that's it from my end today. So we'll meet again in the next session. Thank you.